So we talked about a few parameters already, a few of um, our equations for magnetic circuits, a few of our variables that define how a magnetic circuit work. We talked about flux. So flux, we give it this symbol, which is a capital phi, and flux is a count of the number of lines of magnetic fields. And flux is kind of like current. It's kind of like the effect in an electric circuit. And this is the effect that happens in a magnetic circuit. And then we talked about FM or MMF. It doesn't matter which symbol you use, but that's the cause. That is what induces the flux. So that's kind of like voltage. And we talked about reluctance. So I write reluctance with like fancy R. Reluctance is sort of like resistance or the opposition to the flux in a magnetic circuit. So it is like resistance in a electric circuit. So when we say V equals IR, voltage equals current times resistance, that's like saying FM is equal to flux times reluctance. The reluctance is the opposition that the magnetic circuit is giving to the establishment of the flux. So reluctance is the opposition to magnetic flux. So I like to think of that is negative. It's an opposition. It's saying, well, the more reluctant we are, the less flux you are going to establish in this magnetic circuit. So if it is, say, a circuit made out of plastic, it doesn't want to make that magnetic. It's very reluctant. It is very high opposition to the magnetic flux. So you're probably not going to make a plastic very magnetic at all. But if it is a steel, an iron, say a soft iron core, then it has very small reluctance. It's not very reluctant to the establishment of the flux. So if it has low reluctance, means yes, it's easy to establish those magnetic flux lines. But sometimes we don't like to think about reluctance in the sort of opposition form. Sometimes we like to think about it in the more welcoming way, which is the inverse of reluctance. So it's like in electric circuit, you have resistance, but the inverse of resistance is conductance. So conductance says how much current do I welcome in this electric circuit? Well, we have a inverse of reluctance, and it's called permeance. And permeance is how much we welcome the establishment of magnetic flux. So that's called permeance. It's how much we welcome it. So it's the same thing, but it's looking at it from the opposite point of view. It's the ability to permit magnetic flux. It's saying, yes, I want that magnetic flux. So for permeance, the higher the permeance, the more magnetic flux. So reluctance is how reluctant you are. So if it's higher reluctance, you'd have less magnetic flux. And permeance is how permeable it is, so how much you can make magnetic flux happen. So then we have this important equation that they're just the inverse of one another. So permeance, magnetic permeance is just 1 over reluctance. Permeance is just 1 over reluctance. Do we need permeance? No, because we have reluctance. We can always use reluctance, can't we? This would be Henry, because reluctance is Henry inverted, which is equal to Weber per amp. I like to put turns in there. So this would be a Henry, which is an amp per Weber, but I like to say amp turn per Weber. It's more descriptive. So do we need the new definition, permeance? No, it's just the inverse of reluctance. We could always just use reluctance. But we invented this P for permeance, which is tells us that that we can kind of represent it in the inverse form. So, what's going on here? Oh, thank you. Whoever just wrote that, thank you. You are right. I am wrong. And whoever just did that is awesome. Okay, so let me see. Permeance. See, you know what? I told you, you always have to have a little cheat sheet in front of you, and that I always have a cheat sheet in front of me when I'm teaching this and when I'm doing any example problem. And I don't right now. I slid into this meeting without getting out my cheat sheet. So is this correct now? You can put a check mark beside it if it's correct in both cases. Okay. So great. They are the inverse of one another.
Karen?
Yes.
Can I ask a question? Is the Henry the same Henry as in inductance?
It is. And they
It
are
is?
related, but we're not getting into exactly how they relate, but it is the same Henry as inductance,
Okay.
which you should be learning about right now at the same time, or already learned about. Okay, so now we talked about normalizing before, or maybe it was just the energy system students, but we talked about normalizing somewhere. So what does normalizing mean? Normalizing means, well, I look at something, let's say, I look at here's oh yeah, I talked about it in this class. Here's a large magnet, and here's a small magnet. Which one has more permeance? Remember, permeance is the inviting flux, right? Permeance. Which one has more permeance if they're both made out of the same material? Yes, somebody is writing on this exactly. This one is more. This one is more inviting. It's going to have higher amount of flux, right? This one is going to have less flux because it's smaller. All right. So I think I just accidentally erased something somebody was writing. I'm sorry.
I erased it myself.
Oh, okay. All right. So this is a larger magnet, so more flux, and this is a smaller magnet, so it's going to have a teeny tiny amount of flux. Now, that's sometimes useful. I mean, it's obvious though, if there's more magnetic material, you're going to have a bigger magnet. What's more useful is saying, how strong of a magnetic material is this one compared to this one? So if this is A and this is B, how strong of a magnetic material are they? That does not depend on the size. So how strong material? So if we're asking how strong is the material, it means we need to normalize. And that's just like if you buy a box of cereal, you say, well, how expensive is this cereal? Well, obviously, the larger cereal is going to be more expensive. It's going to cost more dollars to buy that material. But you would have to divide by the amount divide the cost by the amount of cereal that's in each box to see which like spoonful of cereal is more expensive. All right, so yes, more lines of flux are going to be a stronger magnet, but okay, these are both going to establish these lines of flux, but how strong is each material? So what you're going to have to do is you're going to have to normalize, and normalize means divide by something. Oops. Divide by something. And what you're going to be dividing by here is area, is a ratio of area over length. So what you're going to be doing is you're going to look at a little area of each of these, and that area is going to be the same size. Okay, so this and this, you're going to cut this little section out, and you're going to say, and it's the same size. Now I'm going to compare what's the permeance of this cube compared to the permeance of this cube that's exactly the same size. Now I can compare which one is a stronger material, right? Which one is a stronger magnet? Okay, so that's what permeability does. Permeability. Permeability, shouldn't put it in red because permeability is a good thing. So permeability is not permeance. Permeability is mu. And what it does is it looks at the permeance, the permeance of this entire magnet, and then it divides it by length over area, which is the same as multiplying by length. Sorry, you divide by area over length, which is the same as multiplying by length over area. So you have normalized. So you're just looking at that little cube now. So, and then if I substituted in of what PM is, so here's my equation that I just wrote, PM times length over area. If I let the permeance equal 1 over reluctance, which it is, then it would be 1 over reluctance times length over area. So it is the equation then for permeability is length over reluctance times area. That's our equation for permeability. So permeability is a measure of permeance that is normalized for a certain size. So permeability. All right, you're actually normalizing it over a volume, cross-sectional area times length, which is volume. Okay, so all of this is defined. Length is measured in meters. A is a cross-sectional area in meters squared. In magnetic circuits, I said you have to remember all of the equations, plus know all of your units and use all of your units. Your units are what's going to aid you in coming up with the answers. A material's permeability depends on its type, so it is a material property. Okay, so there's a special permeability, and I don't really like it. It's kind of arbitrary that we're making a new symbol for it, but it is called permeability naught. Okay, the small zero in math means naught. So mu naught, which is permeability naught, is permeability of free space. So if you make a vacuum and there's no material in it at all and there's no air, then it's called free space and it has a certain permeability. the permeability of free space. You have to have this on your cheat sheet. That should be in front of you, should be in front of me, should be in front of you for the midterm also, the open book midterm. Permeability of free space is 4 times pi times 10 to the negative 7 Weber per amp turn meter. So 4 pi times 10 to the negative 7 is the permeability of free space. We just use this as a reference number.
I have one question.
Yes, go ahead.
In quiz 3, you asked about one example of donut-shaped core steel magnetic core has a circular cross-section area whose radius is. Okay, you understand that question?
Yes, it's a
So
good one.
yes, I found very difficult to solve it and failed many times. I've passed 4 hours on it, but can you please explain
Oh,
it?
for sure. I'll do an example just like that today, okay?
Okay.
Okay, and you're absolutely right. This all sounds pretty easy. You have your reluctance, your reactance, your permeability, your MMF, and your flux density. Those are your equations so far. It sounds pretty simple, but it's when you apply it that it's actually difficult and time consuming, and there are a lot of tiny things that can go wrong. So remember, I said last time, this is all you're going to learn, but applying it is extremely difficult because there's a lot of ways that we can go wrong. So remember, 4 pi times 10 to the negative 7 is just the permeability of free space. So we expect then, if permeability is how welcoming a magnet is in the establishment of magnetic flux, then we would expect, say, an iron material to be more welcoming, correct? So we would expect an iron material to have a higher permeability, right? So here's another arbitrarily assigned definition, and not by me, but by mathematicians, and this is called relative permeability. All right. And this relative permeability, it just says, well, how permeable is something compared to free space? So when you look at materials, you're going to see values like the relative permeability is 800, for example. Relative permeability is 800, then this means it is 800 times more permeable than free space. And then what would the units be on relative permeability? So what they would be is this unit. So what is this unit here? It's not written very nicely. It's Weber per amp turn meter. But what is a Weber per amp turn? A Weber per amp turn is a Henry. So therefore, this is a Henry per meter. So if I looked at relative permeability, the units would be Henry per meter over Henry per meter. And then those units would cross out. Therefore, it is unitless. Oh, so why does a vacuum matter? Vacuum matters, and I don't pretend to be a physicist, okay? I'm just applying some physics that has been worked out. Why does a vacuum matter? Because the physicists who are trying to define the motion of what or the forces of what magnetic, like magnetic material and the properties of magnetic materials need a definition. And the definition of permeability is based on how much establishment of magnetism or magnetic flux happens in a vacuum. So this is just the standard that has been chosen, and our math is based around how many times more than the standard. So why does a vacuum matter? Because this is a measurable amount that is close to nothing. Okay. This is our closest to nothing. No establishment, no permeability. So this is as close as we get to no permeability. And in this course, there is nothing that is establishes magnetic flux less than that of free space. Okay, so can it get negative? Can permeability actually get less than 4 times 10 to the 4 pi times 10 to the negative 7? In reality, it can happen in our world. We are learning this so that we know electric machinery, and it cannot happen. So we are going to be above that of free space. And this is a value that is agreed upon as a standard to start with. This is agreed upon as no permeability. So now I look at, let's say, plastic. Does plastic establish a magnetic flux? No. So we are going to assume no permeability. Assume that of free space. So assume that the permeability of plastic equals the permeability of free space.
Hello.
Brass. Yes.
Hello.
Yes.
Ma'am, someone is in waiting room.
Oh, there's a waiting room. Oh. I'm not seeing that. I
am
don't
in the
have
class right now.
Oh, you're in. Okay. Yeah, I don't have a waiting room set up. Okay. Sorry if you've had trouble getting in. Thank you. Okay. So plastic it's not very permeable. It doesn't really welcome you to make it into a magnet. So we say that behaves just like free space. Brass, also, you cannot make a magnet out of it. So assume that the permeability, and you need this for your midterm, okay, of brass is equal to that of free space. Cardboard. And I'm saying cardboard on purpose because there are some electrical devices that put cardboard in between pieces of steel. Assume the permeability of cardboard is equal to that of free space. Okay. So for all of these materials, then the relative permeability would then be the permeability of the material over that of free space. And I'm saying that the permeability of the material is that of free space. So it would be unity. So the relative permeability of plastic, brass, and cardboard, and anything else that is not magnetic, I am telling you, use 1 in this course. If you're in a physics major and you're doing your PhD, perhaps you are figuring out if it is exactly 1. I don't know. It might not be. It might be somewhat not exactly unity. But in this class and in practice, in everything that you're doing in the electrical world, plastic, brass, and cardboard are used to stop the establishment of magnetic flux. So they are used as if they are free space. They have no permeability. They do not welcome the establishment of magnetic flux. So I would like you to use that of free space for the permeability. Any questions about this?
Yeah, so we're supposed to just use plastic, brass, and cardboard in place of the free space, like in place of free space, effectively.
No, so the reason I'm telling you this is because you're going to have, let's say, a magnet later on. Later on, a magnet is going to be made. My computer is just freezing up for a minute here. Okay, so later on, a magnet, you're going to make a magnet out of some rows of material, okay? I have one in front of me, but I have trouble showing it to you. So this is going to be iron. And in between the iron, you're going to be, it's actually built with a material in between. And that material is sometimes cardboard or plastic. Okay, so later on, you're going to be, instead of a solid chunk of iron, you're actually going to be building with laminates of iron. So I'll try to show you the core that I have in front of me right now a bit later on, but it's, instead of building with one chunk of iron, you actually build with what's called laminated cores. Okay, and that is because there's these little eddies that get developed, and you want to minimize the eddies, okay? Because a lot of weird stuff happens. So you actually make laminated cores, and the laminated cores are trying to put spaces. But of course, you can't build laminate with air, can you? You want to build it with air, free space. You want to build it with free space. But if you try to build something with free space and then hold it in your hands, it would fall apart, right? So you need to build it with something that acts like free space. So you use brass or cardboard or plastic in order to build up a laminated core. And that's to reduce eddy currents. So that's what we'll talk about later on. And that's called air gap problems. Okay, so we're going to get into a whole series of problems later on that are called air gap problems. By problems, I mean mathematical problems. Okay, so air gaps are built into magnetic circuits, the physical magnetic circuits. They're built in to break something called eddy currents, which is sort of a unwanted effect that is going to make your circuit unpredictable. So that's why this is important to know what the permeability of free space is. Because we can't build with free space, we build with these materials that act like free space. Okay, good question.
Thank you.